the partial sum of a geometric sequence. And the sequence we'll use is this: 1, 3, 9, 27, and so on. And you can confirm that this is geometric. There is a common ratio of 3 for this particular problem. But the partial sum that I want to talk about is just the fifth partial sum. And the fifth partial sum would not be challenging to find directly. All we need to do, remember, is to write the first 5 terms of the sequence down and add them together. And notice I just multiplied 27 by 3 to get the fifth one. And you can do the arithmetic here and find that the answer is 121. But I want to show you an alternate way to get that answer, because it's going to get us to the idea of a formula for the nth partial sum of a geometric sequence. So here's what we're going to do. I'm going to write the fifth partial sum again. And I'm going to write it as 1 plus 3 plus 9 plus 27 plus 81. And here's what I'm going to do now. I'm going to multiply this equation by 3. And I'm using 3 because it's the R value for this problem. So I'm going to multiply this equation by 3 and write it down. So when I do that, I have 3 times the fifth partial sum equals, so I have 1 times 3, 3 times 3, 9 times 3, 27 times 3, and 81 times 3. And instead of writing it right underneath the individual terms, I'm going to move it over. So when I multiply 1 by 3, I'm going to write it right here. And I'm going to multiply 3 by 3 and write it here. 9 times 3 is 27. 27 times 3 is 81. And 81 times 3 is 243. So I have 2 valid equations. Now I'm going to subtract those 2 equations. All right, I'm just going to write this. So remember, we're subtracting. So I have 1s sub 5 minus 3s sub 5, which is negative 2s sub 5 equals, now remember we're subtracting, 1 minus 0 is 1. But now notice what happens. We have 3 minus 3, they're gone. 9 minus 9, 27 minus 27, 81 minus 81. And finally, 0 minus 243. So all I have left is 1 minus 243 when I subtract these 2 lines. And I can do some arithmetic there. And I have negative 242. Divide by negative 2. And I get 121. And notice it's the same answer we got here. And you could look at that and say, well, shoot, that was a lot harder than the addition that we did just adding them up directly. But I wanted to show you this because deriving the formula will be much like this. And I just wanted you to see it with numbers first. So here we go. We're going to come up with the formula for the nth partial sum of a geometric sequence. So we'll let our sequence just be this: a sub 1, a sub 1r, a sub 1r squared, and go all the way out to a sub 1r to the n minus 1. So notice our sequence: first term, second term, third term, nth term. So the sum of those first n terms are a sub 1 plus a sub 1r plus a sub 1r squared, and keep adding And here's our nth partial sum of our geometric sequence. Now remember what we did on the previous example? We multiplied this line by r. So let's multiply this equation by r. So we have r times s sub n equals. And when I multiply this a sub 1 by r, I'm going to write it down here, just like we did on the previous example. I don't need a little plus sign there. I have a sub 1 r plus, multiply this term by r, and so on. And we have a sub 1 r to the n minus 1. And when we multiply this term by r, we'll have a sub 1 r to the nth power. Don't forget that's what happened. Remember here on our previous example, we ended up multiplying 81 by 3. Here we're multiplying a sub 1 r to the n minus 1 by r. And now we're going to subtract. And when we do that, we have s sub n minus r times s sub n. Okay, let me write that down. And on the right-hand side, we have a sub 1 minus, and there's no term there. But now we have a sub 1r minus a sub 1r. So these terms will go away. And we'll subtract these, and we'll subtract these, and all of the terms in between, and we'll have that, minus a sub 1r to the nth. Don't lose sight of what we're trying to find. We're trying to find a formula for the nth partial sum of this geometric sequence. So we're trying to solve for s sub n. And notice we have an s sub n in both of those terms, so I'm going to factor out that s sub n. And we'll just have 1 left from this term, minus r. And on the right-hand side, I could leave it that way, or I could factor out the a sub 1. I prefer to factor out the a sub 1, so I'm going to do that. And finally, we're going to divide both sides by 1 minus r. And we'll have this. S sub n equals a sub 1 times 1 minus r to the nth divided by 1 minus r. And of course, r can't be 1. If r were equal to 1, we would have a 0 in the denominator. So here's our formula for this for the sum of the first n terms of a geometric sequence. So let's do a few problems. Let's start with this one. Find the sum. And I could go straight to the formula. I just find it handy personally to write out a few of the terms. It just helps me think it through. If we only have 7 terms for this particular sum, start with k equals 1. Notice that would give you a 0 exponent here. Negative 5 to the 0 is just 1. So we would have 4 times 1, or just 4. Our next term we would get if we substituted k equals 2 in. So our exponent would become a 1. We'd have 4 times negative 5, or negative 20. And I hope you can see that this will alternate from plus to minus and plus to minus as we write more terms. I'm not going to fill in any more. Let's put in the last value of k equals 7. Negative 5 would be raised to the 6th power. And of course, that would mean we'd have a positive value. And you can punch that in your calculator, and you'll find that you get 62,500. Again, that's not necessary to write these terms out. I just like to do that. It just gives me a better sense of what I'm doing and what I'm looking for. I'm looking for this sum. Now let's use our formula, because we know this is geometric. because we're multiplying by -5 times another -5 times another -5. It is geometric, so this formula is valid. Let's write it again. S sub n equals a sub 1 times 1 minus r to the nth divided by 1 minus r. So we're just going to practice using the formula. So the seventh partial sum, because we know there are 7 terms starting with k equals 1 and ending with k equals 7. We need the first term, which we know is 4. We substitute in our r value. R is -5. And we're going to put in an exponent of 7. There's n, r to the nth power. So we're going to raise that to the 7th power. Divided by 1 minus, and you do have to take care. I find that some of the mistakes that people make are not being careful with the signs here. So if we raise -5 to the 7th power, you will have a negative value. So we have 4 times 1 minus a negative value means we're going to have a plus. So you can raise 5 to the 7th power, and you'll find that it's 78,125. Divided by 1 minus -5 is 6. And let's do a little bit of arithmetic before I grab my calculator. I'm going to add the 1 and the 78,125, so I have 78,126. And although it's not necessary, because we're going to grab a calculator in just a moment, I see a 4/6 and I can't help myself. I reduce it and make it a 2/3. And now you can grab a calculator, punch that in, or do it by hand. And you'll find that you get 52,084. And if you found all the terms here and did the addition, you could confirm that that is in fact the value. Let's do another one. Let's find this sum. And notice we can confirm that it's geometric. We multiply by 2 and by 2 and by 2. So our formula is first term times 1 minus r to the nth divided by 1 minus r. Now the issue on this one is, although we know the first term and we know r, we don't know how many terms we have. So we're going to use the relationship that we have between the nth term and the first term to find it. In other words, back to our other formula, a sub n equals a sub 1 times r to the n minus 1 power. So our nth term, this one, is 256. Our first term is 1, and we have r, which we know is 2. Let me substitute in the 2, to the n minus 1 power. So if we just take care of the 1, and I write it a little neater so that you can see that that's actually a 2, we have 256 equals 2 to the n minus 1 power. Now, you could use logarithms to solve this equation, but there isn't any need to. If you play around with powers of 2, you'll find that 256 is really 2 to the 8th power. And if you can write two exponentials with the same base raised to a power, we know that those exponents must be equal. So we know 8 equals n minus 1. Add 1, and we have n equals 9. So we know that 9 terms are being added together here. So now we can use our formula. So the sum of the first 9 terms is equal to the first term times 1 minus r to the 9th power divided by 1 minus r So we have 1 minus 512 over negative 1. Continue simplifying. And we have 511 as our sum. Let's do one last problem. It looks like this. And I wanted you to see a problem where the R value is not an integer. There's no requirement that our R value be an integer. It can be a number like -1/2. I'm going to write the first term or two and the last term, again, not necessary, but I just like to. So I substitute in k equals 1. So I have -1/2 to the 0 power. We know any number except 0 raised to the 0 power gives us a 1. Then I put in k equals 2. 2 minus 1 is 1. -1/2 to the first power is just -1/2. And continue. And finally, we would substitute in k equals 10. 10 minus 1 is 9. And if you raise -1/2 to the 9th power, you'll find that you get -1 over 512. So this is what we're trying to add together. So here's our sum. Let's use our formula again. Let's write it out. If we write it out each time we use it, we'll get it memorized. The nth partial sum is the first term times 1 minus r to the nth divided by 1 minus r. Our first term is 1. We have 1 minus our r value is looking at us right here. It's -1/2 to the, and we know how many terms we've got. We started at 1 and ended at 10. That means we have 10 terms divided by 1 minus -1/2. So we have some arithmetic to do here. Let's see, this is just a 1. I won't write that on my next line. But I have 1 minus, now this -1/2 is raised to the 10th power, so that'll be a positive value. So I have 1 minus whatever this value is. And you could confirm that it's 1 over 1,024. And in the denominator, I have 1 minus -1/2, which becomes 1 plus 1/2, or 3/2. Let's see, we have a little more arithmetic to do. Let me come over here. 1 minus 1 over, let's see, 1 minus 1 over 1,024. If you get a common denominator, you'll find you have 1,023 over 1,024. And we're dividing that by 3/2. And of course, that means we're multiplying by the reciprocal. And I want the exact value here. That's why I'm not grabbing a calculator and getting a decimal approximation. I want the exact value of that sum. And so now I can do some arithmetic and reduce. 2 goes into 2 once. 2 goes into 1,024 512 times. Similarly, 3 goes into 1,023 341 times. And when we multiply across, we have 341 over 512. And we have the sum of this expression right here.